Hello everyone, today I'm going to talk about the volcanic, sedimentary and deformation history of the Winter Lake Greenstone Belt within the Slave Craton in Northwest Territories. I'm Valentin, I'm a PhD student under the supervision of Dr. Barton and Dr. DeWolf with the collaboration of Bernadette Knox from the NTGS. I have two fellow master students with me on this project, Dawson Stone and Emily Macmillan. Here's a quick outline about the thing I'm going to talk today, with a nice picture of the Winter Lake Belt area. The Slave Craton is a major block of the Precambrian core of the North American plate, located on the western part of the Canadian Shield. It is one of the 35 Archean cratons preserved around the world. The Slave Craton originated from the break of a much larger late Archean landmass called Cairnland, or a smaller landmass referred to as supercraton Sclavia. The amalgamation of the Slave Craton with the Ray Craton started at 2 Ga, initiating the growth of Laurentia from 2 to 1.8 Ga, probably within the context of the formation of Earth's first modern supercontinent called Nuna. The Slave Craton can be considered as a far-traveled fragment of crust relative to other cratons in Laurentia. The Slave Craton is approximately 35,000 square kilometers in size. It hosts Earth's oldest intact rocks, the Agastine gneiss. Supracrustal rocks can be divided into 4 sequences of different ages. The dominating supracrustal rocks are represented by volcanic and grey-rocky mudstone sequences that accumulated between 2.72 and 2.60 Ga. The Yellowknife Greenstone Belt has served as a template for the stratigraphy of greenstone belts and the evolution of the Slave Craton. On the right side we have the lithostratigraphy with the central slave basement complex at the bottom and the Yellowknife supergroup, supracrustal rocks on top of the basement. And it's composed of central slave cover group quartzite, the camp group pillow to massive ptoleitic basalt. Then we have the benting group, felsic intermediate volcanic rocks, the Burwash formation, turbiditic clarity mudstones, and then we have the thin orogenitic conglomerates on top. Few models have been proposed for the evolution of the Slave Craton. Two prevail. The first one on the left is the tectonic accretion of juvenile Neo-Archean terranes to a composite of Paleo-Meso-Archean continental nucleus model. And on the right side, we have the supra-subduction zone setting model. In the Slave Craton, it is generally assumed that greenstone belts developed during a single tectonic environment over 30 to 50 million years, between 2730 Ma and 2690 Ma. So where would the Winter Lake Belt be on those models? Well, for the first one, the volcanic rocks of the belt would represent an abducted oceanic crust on the central slave superterrane, Meso-Archean gratinoid basement, together with later sedimentary rocks. According to the other model, the belt would be situated in a supra-subduction zone setting. The supracrustal rocks would be emplaced on a rifted basement, with volcanic rocks emplaced in an arc to a rifted arc environment, with later sedimentary rocks deposited in a back arc setting. So the Winter Lake Belt is situated 250 kilometers north-northeast of Yellowknife, is striking northeast-northwest, has a synformal geometry, mafic to felsic volcanic rocks and sedimentary rocks that are sedimented, surrounded by 2.9 to 3.3 Ga granitoids that are interpreted as basement. This is a simplified geological map of the Winter Lake Greenstone Belt. One of my hypotheses is that the origin of the Winter Lake Belt is considered autochthonous One way to support this hypothesis would be to study the temporal and petrogenetic link between mafic dikes and in the gneissic basement and overlying metavolcanic sequence. The red squares are mapping areas. This is Big Bear Lake area, the New Baking Lake area. So both are where I've already been in the field season 2019. And then for the next field season, it will be on Sherpa Lake and Puzzle Lake. As you can see on the map, several mineral showings have been already discovered. My hypothesis concerning mineralization is that the mineralization in the belt is a VMS style mineralization. One way to test this hypothesis would be to demonstrate its occurrence in volcanic sequence, its stratiform nature, and analyze the base metals composition of the mineralization. So I'm going to go through the lithostratigraphy of the belt. At the bottom, of course, we have the gneissic basement rocks. Then we have the New Beginning Formation, thought to be the oldest supracrustal rocks in the Slave. We have the orthokwarsite from the North Shore Formation, a craton formation made of chromatic basalts and schist. Its position in the lithostratigraphy is not very well known, so dating will be critical. We have the snare formation, consisting of mafic volcanic sequence of pilot flows and massive units. Then we have the turbiditic sedimentary rocks, the Archean formation, and then the Providence formation, which is a very local thin unit of felsic and mafic volcanic rocks. We have the Sherpa formation, a polymictic conglomerate, and intrusive suites that are intruding the supracrustal rocks and basement. One of my hypotheses is that I envision the genesis of snare, credit, Archean, and Sherpa formation supracrustal rocks in a back arc basin environment. One way to test this hypothesis would be to investigate the degree of crustal contamination, determined through trace element content and samarium-neodymium isotope geochemistry of the mafic volcanic sequence. Another hypothesis is that in the Winter Lake belt, the Yellowknife supergroup rocks are overlying the Central Slave basement complex. In order to do that, I will have to correlate the slave nomenclature on the left with the lithostratigraphy on the right. What's interesting about mafic rocks in the Winter Lake belt is that on the west margin, the geochemical nature of mafic to tholeiitic to calcareous basaltic rocks changes from the bottom to the top. So mafic rocks at the base have been influenced by supra-subduction zone or by a component of continental crust, whereas the top suggests little to no crustal contamination. On the east side, mafic rocks are tholeiitic and have a mob-like trace element pattern, suggesting neither eruption in an arc setting or crustal contamination by the underlying felsic rocks. A small overview on the structural geology of the belt. D1 deformation event postdates turbiditic sedimentary rocks but predates the younger conglomerates. F1 generation of faults predates the dominant northeast striking foliation S2. There is high strain zones, especially at the contact between supracrustal rock and basement, folded about F2 folds. The overall formal geometry of the Winter Lake belt is thought to be the result of D2 deformation event. An overview of the economic geology of the belt. The snare formation is known to host massive sulfide bending iron formation with grade of gold. When we have a potential exploration target for VMS deposit for Providence formation. The rocks within the belt have been metamorphosed through the green schist to lower amphibolite facies. Metamorphic mineral assemblages are indicative of high temperature and low to moderate pressures. Cordierite, orthophyllite, and tremolite are thought to be pre-metamorphic hydrothermal alteration mineral assemblages. The dominant foliation forming deformation event happened at the same time as the peak metamorphism. Here an overview on my overall research objectives. So I plan to understand the origin, geodynamic evolution, and economic potential of the belts, set up the winter-like belt rocks within the slave craton context linked to Archean tectonic processes, incorporate those rocks within the slave nomenclature, create an overall synthesis of the belt using the results from the master's thesis to refine my hypothesis and further investigate their results. In order to do that, I have specific research objectives. So my first objective will be to study the stratigraphy. I'll map at 1 to 10,000 scale at 4 locations. And with the help of thin volcanic fault and thrust mapping and uranium-led geochronology, the results will explain the tectonostratigraphy and possibly stratigraphic duplications. To test the hypothesis that the snare and credit formation rocks formed in the back arc basin environment, a petrogenetic study will be conducted with the help of the first master student. To test the hypothesis that the meta-sedimentary rocks are also representative of a back arc basin depositional environment. A second master project will be conducted on will conduct a basin and provenance analysis on meta-sedimentary rocks. I plan to demonstrate the existence of the regional decollement along the basement cover contact by the support of structural and geochronological data. Only then it will be possible to develop a consistent kinematic framework for the basement cover high strain zone and debate its tectonic significance. To test the hypothesis that the mineralization in the belt is a VMS style mineralization, I plan to map and sample selected showing across belts and compare their size, length, width, shape, distribution, and orientation. Here's some preliminary results with the geological map from the New Beginning Lake and the location and the picture from the mafic seals within the granitoid basement. Next is a nice outcrop on the North Shore orthoquartzite. Here's a picture of a handsome field assistant sampling a mineralization, the mineralization within the snare formation. And then we have a nice picture of the Archean formation, the geobiditic meta-sedimentary rocks. Next is the geological map of the Big Bear Lake area. With another picture of the Archean formation with a nicely banded geobiditic meta-sedimentary rock. Then we have a cross-bedded sandstone bed within the Sherpa formation, within the conglomerate. Speaking of conglomerate, we have the mineralization within the conglomerate next to the contact with the snare formation. Then we have a very nice outcrop of lichen cover and a nice picture of the ultramafic intrusion that is easily distinguishable by the reddish surface. Here are some thin section pictures. So as you can see, we have some garnet, biotite, amphibole, with chlorites, mainly actinolites and hornblends coming tonight. And as you can see, it's there are mineral assemblages representative of green schist to amphibolite metamorphic facies. It's also possible to see on picture B crenellation cleavages that are thought to be indicative of two distinct compressional deformation events. Next slide will be about my geochemical results. So I've applied few filters to select the least altered samples to be able to use the following trace to be able to conduct a trace element geochemistry study. I'll be using the CCPI and AI plot. I was able to select the final least altered sample within the least altered box and identify a cluster of samples outside the box, which illustrates the carbonate alteration effect on the whole rock composition. Then I had to check the mobility of major and trace elements before using the following diagrams. So I plotted Ti and Y and YB plot against zirconium, and they have the specificity of generating two distinct increasing trends. Thorium and neodymium points follow an increasing trend, and vanadium values define a decreasing trend. At the bottom of the graph, we can see that SaO2 and NaO2 graphs have very scattered data points. Since there is no significant mobility of these trace elements, I used the following diagrams. The first diagram, we can see there are three rock types: basalt, andesite, and rhyolite. These three rock types are present in the New Beginning Formation. Snare Formation has only basalt and andesite. Intrusions are gabbros and diorite. The basalt, andesite, and rhyolite New Beginning Formation and gabbro intrusion have an intermediate to calc-alkaline affinity. Snare Formation basalts and andesites have toleatic to transitional affinity. Basalts and gabbros have an island arc and mid-ocean ridge geochemical signature. It's also possible to see on the next diagram that there are three main affinities for mafic rocks in the belt: volcanic arc calc-alkaline basalts, volcanic island arc toleatic basalts, and normal mid-ocean ridge basalts. I also tested my trace element geochemistry results using primitive mantle and chondrite tomalized trace element diagrams. The snare and credit formation basalt are characterized by flat to gently sloping patterns on both diagrams. They have a weak negative niobium anomaly relative to thorium and lanthanum. New beginning and snare formation rhyolites and andesites are enriched in light rare earth element relative to heavy rare earth elements and have a European negative anomaly. They have a strong negative niobium anomaly relative to thorium and lanthanum, and a strong titanium anomaly. Primitive metal like chondrite normalized trace element diagrams for gabbroic rocks show enrichment in light rare earth element relative to heavy rare earth elements. A strong negative niobium anomaly relative to thorium and lanthanum is also present. So it is possible to say that there are significant mobility of major elements within the belt. The snare and credit formation basalts of mineral assemblages very typical of green schist to amphibolite facies. Using the primitive metal chondrite normalized diagram, it's possible to say that they are arc-like geochemistry and to a mob-like geochemistry signature for basalts. There are three possible signatures as well using a different diagram: the volcanic arc calc-alkaline basalts, volcanic island arc toleatic basalt, and normal mid-ocean ridge basalt affinity. Andesite and rhyolites of the New Beginning snare formation, together with gabbro intrusion, have geochemical signatures suggesting contamination from continental crust. And the representation of gabbroic intrusion on the original map by Rabi and Grant was underestimated, and the New Beginning formation was overrepresented. A quick summary of my future work. I'm going to generate a geochemical, isotopic, and geochronological database of volcanic and sedimentary rocks. Investigate the geochemical differences between the mafic rocks from the east and west side of the belt. establish a temporal and petrogenetic link between the dike swarms in the basement and the volcanic sequence, conduct a basin and provenance analysis of the meta-sedimentary sequence, start a structural study of the high strain zone between the basement and supracrustal rock limit. And I plan to constrain the pressure temperature condition of each deformation phase to model the entire winter lake belt tectono-metamorphic evolution and create an Archean continental crust geodynamic evolution model. Finally, I will identify sources of precious and base metal of the mineralization, which is necessary for my winter lake belt VMS genetic model. I'd like to acknowledge all those wonderful people. I couldn't be here without them. Here are my references. And thank you for your attention. If you have any question, feel free to leave a comment on YouTube or join me on the WebEx meeting. Thank you.